Okay, now we're doing section 3.3 of physical chemistry. In the previous section we did a Carnot cycle. Now we're going to talk about any arbitrary cycle. I drew this as neatly as possible, but there's a ton of information here. We have a PV diagram. This circle represents any arbitrary cycle. I tried to draw it as a perfect circle, but technically the shape doesn't matter as long as it's a closed cycle. Now all these somewhat diagonal curves that are dashed, these are reversible adiabats. Now our cycle then, we're actually going from state, what is it, M to N. No, we're going from A, B to C to D. That's the cycle we're trying to analyze. Now what instead we've done is we've drawn some isotherms connecting these adiabats. So we're going to end up with actually point R, S, and M and N. These are actually on isotherms and adiabats. So the cycle MNRS, that's going to be a Carnot cycle like we've seen before. Now, if I didn't shade it in very well here, but basically we've made a couple of triangles. These two shaded insides that are opposite each other. The area under AMNB is going to be the same as the area under AB. And so, yeah, the area under all this is equal to the area under all that. So, the area under the curve, remember this is PV, so the integral of PV is reversible work being done on the system. Now remember the area under AB then is also the reversible work done on the system. So the work, if you do under AM and B, is the same as AB. Now remember from the first law that delta U is equal to Q plus W. Now Q from A to M is 0 because A to M is an adiabat. Remember all these diagonal lines, the dashed lines are adiabats. Now QBN is equal to 0 because Bn is also an adiabat. Now we've said before QAMN and B is equal to QMN, and that's equal to QAB. And likewise QRS is equal to Q of CD. Now remember our whole our Carnot cycle here would be all the way from M to N to, that's back, yeah, S to R and then back to N. Obviously you have to end up where you started for it to be a complete cycle. Physical Chemistry, Chapter 3, Section 4. Now, the 10th type of entropy change we're going to look at is when we mix two different inert gases. Now, this one's going to take a couple of different slides because we're going to have to look at a couple of different steps here, break it down into simpler steps. And we're going to assume this is done at constant temperature and pressure. Now, this is our initial system. We have two different gases, gas A and B. I drew them in different shapes so you can tell them apart, but obviously they're all probably spherical if they're inert. But anyway, so we're keeping them separate with a membrane for now. So each one, they've got the same temperature and pressure, P and T, but they've got their own volume. So we have the volume of A and the number of molecules for A. And then we have the volume for B and the number of molecules for B. What we're going to do is we're going to let these mix together. So the entire system is going to have both gas A and gas B. Now we said the change in temperature is equal to 0, and we know for an ideal gas that U is a function of temperature only, therefore we're now going to know that delta U is equal to 0 for this volume expansion. And of course, for this, Q is going to be equal to minus W then, since this is non-adiabatic and constant temperature. So the entropy for the first step, which is just the expansion actually of the volume, is going to be, of course, the change in entropy of step 1. It's going to be the change in entropy for gas A plus the change in entropy of gas B. And we showed before that expansion causes an increase in entropy. So the increase in expansion for A is going to be NA times R times the natural log of the total volume divided by the initial volume of A. And then the increase in entropy for B will be NB times R times the natural log of the total volume divided by the initial volume of B. So that's going to give us an entropy change just from the expansion. Then secondly, we need to look about, okay, now that we've allowed them to expand, what about actually mixing them? So we have a reversible isothermal mixing of the expanded gas. Now again, we know that delta T is equal to 0, so we still know that for this step 2, that delta U is equal to 0. We're also saying that work is roughly equal to 0 because the pressures, we started out with them the same. Mechanical equilibrium, I guess. And Q is equal to 0 because W is equal to 0 and delta U is equal to 0. More on the next slide. Okay, continuing on chapter 3.3 of physical chemistry, we're talking about arbitrary cycle, and we're doing it by comparing it to a Carnot cycle, which we already analyzed in section 3.2. Now I redrew it a little bit bigger, hopefully you can see better now. So this is a PV diagram. The circle represents our arbitrary cycle, or more specifically, we're going cycle A, B, D, C, and back to A. And notice we drew a couple of adiabats. These are reversible. And we also connected the adiabats with reversible isotherms. Isotherm R and S and M and N. And what we said is that the area in here is equal to the area in here, and that the area in here is equal to the area in here. Now, there's a few things we could say about this. One is that delta U going from A, M, N, B is equal to delta U, A, B. The reason we know that is because U is a state function, so the path does not matter. We also remember from the first laws that delta U is equal to Q plus W. Therefore, we can say that the Q from A, M, N, B is just equal to the Q from A to B. So the reason we could say that, of course, is that Q A to M and Q from N to B are both equal to 0 because they're on adiabats. Let's see here. And then likewise, we can do the same analysis for down here, just to say that QRS is the same as QC of D. Now, remember what we talked about during the Carnot cycle, how we showed that Q over T is a state function. Therefore, the cyclic integral is going to be equal to 0. So we're going to end up with Q of NB. Wait, would that be NB? That should be NN. Okay. Actually, it should be QAB. How does that sound? All right, so QAB over the temperature Mn plus the QDC over the temperature SR is going to be equal to 0. Again, that's because this is a state function. Okay, continuing physical chemistry, chapter 2.3, or 3.3, we're talking about an arbitrary cycle again, and we showed in the previous slide how we can divide it into a Carnot cycle. So what we're going to do for the overall cycle, then we can just divide it into cycles that are infinite number of adiabats. The cycle we want to analyze, we'll divide it into infinite number of adiabats, such that the temperature at A is roughly equal to the temperature at B for each cycle. The temperature at M and to N is roughly equal to the temperature at A to B, and the temperature at R to S roughly equal to D to C, and so on. And we showed how the dQ at AB divided by temperature AB plus dQ dC over the temperature dC has to be equal to 0 because it's a state function, and we're doing a cyclic integral. So the cyclic integral of dQ reversible divided by T is equal to 0. And the T is, so this applies, we showed that was for a Carnot cycle, now we know this is true for any cycle too. But anyway, so remember this is the temperature at which the heat is transferred. Be careful because T won't be constant in your cycle overall. And since this is equal to 0, we know that this is equal to a state function. Now remember we define capital S as entropy. ds is equal to dQ reversible divided by T. And T must be an absolute temperature such as kelvins. You can't use degrees such as Celsius. So integrating that gives us delta S is equal to Q reversible divided by temperature. Okay, we're continuing physical chemistry, chapter 3.3. We're talking a little bit more about entropy. We just did some closed cycles. Okay, so we got delta S is equal to Q reversible divided by the temperature. And you're probably wondering, why do we even have Q here? Why not W? since Q and W, they're both not state functions, what difference does it make? It does make a difference. Remember that work is organized motion in the surroundings. It's something moving together. It's orderly motion of atoms or molecules in the surroundings. Now Q, on the other hand, heat, this is actually disorganized motion or disorderly motion of atoms and molecules. Now, entropy, it goes with randomness, not organized motion. And the reason you're dividing by T is because that takes into account the existing entropy in the system. If it has a higher temperature, it already has a lot of entropy. If it has a lower temperature, it already has a less entropy. Okay, continuing on physical chemistry, chapter 3, section 3, more about entropy. If you add heat at low temperature, it's kind of like a sneeze in a quiet library. Let's calculate delta S, assuming we're going to add 100 kilojoules at 273 kelvins. We want the answer in joules per Kelvin, so we're going to convert from kilojoules to joules, and that gives us positive 366 joules per Kelvin. Obviously it has to be positive because we're adding heat to the system, which increases entropy. Now adding heat at low or higher temperatures is more like a sneeze in a quiet city. It's not as noticeable. So we're going to calculate delta S again. It's still 100 kilojoules, still going to convert to joules, but this time we're going to use a higher temperature, 373 kelvins. Notice that we're going to get only positive 268 joules per Kelvin for the exact same amount of heat. And the difference is because we did it at higher temperature. Now delta S, remember, is S at state 2 minus S at state 1 because it's a state function. Or put another way, it's the integral from state 1 to state 2 of dq reversible divided by T. Now this is for a closed system, and this is how you calculate it for a reversible process. Now one thing to keep in mind though, of course, any isolated system is also closed. So all these calculations we did for a closed system will still be true if you happen to have an isolated system. Now, let's say we go from state 1 to state 2. We've done all these calculations for delta S reversible, but delta S is a state function. Therefore, it has to be the same result as if you did it delta S irreversibly. So delta S reversible is equal to delta S irreversible. And we can say that because entropy is a state function. Okay, continuing on in physical chemistry, chapter 3, section 3, we're going to talk more about entropy. We showed last time how entropy is a state function, but just to refresh your memory, let's say you're going from state 1 to state 2. So we have the entropy at state 1, entropy at state 2. If we do it reversibly, you can think of that as a straight line, although really it doesn't matter as long as you do it slowly. Irreversibly, you can think of that as zigzagging, but again, it doesn't really matter. Irreversibly just means so fast or something that it's not in equilibrium. But either way, you're getting from state 1 to state 2, and S is a state function. Therefore, delta S must be the same. And S is a state function. It's also extensive, by the way. For example, let's say we have a system, we divide it into two parts, over here and over here. So we would have the entropy over here would be the dq reversible for 1 divided by temperature, and the entropy over here would be the dq 2 reversible divided by temperature. We're obviously just going to assume they're at the same temperature for now because it's at thermal equilibrium. So ds for 1 would be dq1 over t, and ds2 would be dq2 over t. So the ds for the whole system, SYS is system, remember, is just ds1 plus ds2, or dq1 over t plus dq2 over t. So if you integrate that over a certain amount of, time or whatever for a process, then you'll get the change in entropy is equal to the change in entropy for part 1 plus the change in entropy for part 2. Or put another way, the total entropy of the system is equal to the entropy of part system side 1 plus the entropy of the system side 2. So S is an extensive quantity. Now, for comparison, just refresh your memory, density is an intensive quantity. So you couldn't add up the density here to get the density here and get total density. That would not make any sense. So you can add up extensive quantities. You can't add up intensive quantities. Now there is an intensive form of entropy, and that's the molar entropy. Just take entropy divided by N. Since entropy would have joules per Kelvin or calories per Kelvin, the intensive form would be joules per mole Kelvin or calories per mole Kelvin. Continuing on chapter 3 of physical chemistry, we're just now starting section 4 of chapter 3. We're talking more about entropy, and now we're going to come up with ways to calculate the entropy change for different types of processes, just like we did for state functions near the end of chapter 2. Now we already know that the differential of entropy is equal to the differential of the reversible heat divided by temperature. And obviously, we didn't write SYS for system. That's always implied if we don't specify surroundings or universe or anything else otherwise. So integrating that, we're going to get the total change in entropy is equal to the integral from state 1 to state 2 of the reversible heat divided by temperature. And of course, entropy is a state function, so if we find a reversible way to calculate the entropy, we know that's also got to be equal to the irreversible way to calculate the entropy. Now, probably the most obvious case, of course, is a cyclic process. Since entropy is a state function, for the cycle, any state function, the change is going to be equal to 0. So the change in entropy is going to be equal to 0 for any cyclic process, such as the Carnot cycle. Now, another simple way is the reversible adiabatic process. By the definition of adiabatic, dq reversible is equal to 0. Therefore, dq reversible over t is equal to 0. Integrating, that's going to be 0. So we have delta S is equal to 0. The third type that we're going to look at is also the reversible phase change at constant temperature and pressure. Now we know Q reversible, we're at constant pressure, so we can call that QP. And we've shown before that that's equal to the change in enthalpy. Remember, capital H is enthalpy, not hydrogen. And this can also be, since we're talking about like a phase change such as melting or boiling or something, that's called the latent heat of transition. So coming back to our formula for the change in entropy is the integral from state 1 to state 2 of the reversible heat divided by temperature. We said that temperature is constant, therefore we can pull that out, and we have 1 over T times the integral of dq reversible. So that's going to be just equal to the total heat reversible divided by temperature, which we said just now is equal to the QP divided by T. Therefore, the change in entropy, total change for our phase change, is going to be the change in enthalpy divided by temperature. You should be able to tell from this formula then that if the latent heat of transition is positive, then the change of entropy is going to be positive. And likewise, if the latent heat is negative, then the change in entropy is going to be negative. So what this tells you is that if you're melting, you're increasing entropy of the system. If you're freezing, you're decreasing the entropy of the system. Likewise, if you're boiling, you're increasing the entropy of the system. And if you're condensing, then you're going to be decreasing the entropy of your system. Continuing on physical chemistry, chapter 3, section 4, we're talking about different ways to calculate entropy. So the fourth way is if we have a reversible isothermal process. Remember, isothermal means that delta T is equal to 0, but remember, pressure is not necessarily equal to or constant. So we can pull the 1 over T out of the integral since it's a constant. So we just end up with delta S is equal to 1 over T times the integral of dq reversible, which becomes then just the reversible heat divided by temperature. For a perfect gas, reversible change of state, remember, everything could be changing, like volume 1, temperature 1 to volume 2, temperature 2. This is going to be a little more involved. So we're going to start with the first law, which says that dq reversible is equal to du minus dw reversible. So remember, this is heat, internal energy, minus work. So we're going to substitute out some definitions here. So we could get dq reversible. For du, we're going to substitute the heat capacity constant volume with respect to temperature. And for work, we're going to substitute out minus PdV. Remember, double negative makes a positive in this case. And then we're going to take the ideal gas law and substitute this pressure to get nRT over V. So that way we have the same variable here to integrate. Now we're going to take all this and divide by temperature. So we're going to get dq reversible divided by temperature is going to equal to the heat capacity divided by temperature times the differential of temperature plus nR over V times the differential of V. Now we can integrate that. So we're going to get the integral of dq reversible divided by temperature, and that's equal to the integral of the heat capacity, constant volume, as it changes with temperature, divided by temperature, with respect to temperature, plus the integral of nR over V with respect to V. Of course, the integral of dq reversible over t we defined as delta S. We still have this integral, we'll talk about that in a bit. And then the integral of this, we know nR are constants, so we pull those out. And the integral of 1 over V dV is just the natural log of V. So we've got volume 2 over volume 1. Now that's our final answer if CV does change the temperature. If CV is constant, then we can simplify this some more. Well, notice we're going to use the squiggly equals here to say it's approximately equals, because now we're just assuming that this is constant. So we get delta S is roughly equal to the heat capacity at constant volume times the natural log of temperature 2 over temperature 1 plus N, the number of moles, times R, the gas constant, times the natural log of volume 2 over volume 1. Continuing on physical chemistry, chapter 3, section 4, we're talking about different ways to calculate the change in entropy for a process. So number 5, we're talking about, we already showed calculations, the formula for reversible change of state for a perfect gas. So we got two terms. One was nR natural log of V2 over V1. If V2 is greater than V1, meaning the system is expanding, then this term is going to be greater than 0. We also got the other term, the integral from state 1 to state 2 of CV of T over T dt. And if temperature 2 is greater than temperature 1, then this integral is going to be greater than 0. What this should tell you is that if the system is expanding, that's going to increase the entropy of our system. And likewise, if the system is being heated up, that's going to also increase the entropy of the system. So to summarize, the change in entropy increases when temperature increases or volume increases. Okay, now 6, we're going to talk about an irreversible change of state in a perfect gas. Now we know that S is a state function. Therefore, if you come up with a reversible way to calculate the change in entropy, it must be equal to the irreversible change in entropy, because we showed that any state function is not path dependent. But keep in mind, Q heat is path dependent. So even though our delta S is going to be the same, that doesn't mean that our Q reversible is going to be the same as our Q irreversible. Now the 7th type of process we're going to talk about is a constant pressure heating, assuming no phase change, of course. So we know that dq reversible, we're constant pressure, so we can write that as dq sub P, and that's going to be equal to the heat capacity constant pressure times the differential to temperature. And we also know that solving for dq reversible, that's equal to TdS. So starting with our calculation of entropy in differential form, ds is equal to dq reversible over T. Substituting that in, we get, therefore, that ds is equal to Cp dt divided by T. So we want to integrate that to get the total change. The integral of ds, of course, is just delta S. So the integral of this is going to be integral from temperature 1 to temperature 2 of C of P divided by T with respect to T. Now, if we assume that Cp is constant instead of a function of temperature, then we can pull that out of the integral. And we just get delta S is equal to Cp times the natural log of temperature 2 over temperature 1. Continuing on chapter 3 of physical chemistry, section 4, we're talking about different ways to calculate entropy for different processes. Now we're going to do an irreversible phase change. Let's say we have some liquid water, and somehow it's at minus 10 degrees Celsius in 1 atm, which is below its freezing point. If somehow we were to tap it or something, it's going to spontaneously freeze and become a solid H2O at the same temperature, minus 10 degrees Celsius in 1 atm. Now, we don't really have a way to calculate this directly, but if we find a reversible process that does the same thing, we can do that instead. So what we've done is broken it into several parts. One, we're going to heat it up to 0 degrees because we know how to heat Then we're going to freeze it at 0 degrees, because we know how to calculate that. Then we'll cool it back down to minus 10 degrees Celsius. Now we can calculate the delta S for all three of these parts. And we know that that delta S has to be the same as this delta S, because S is a state function. Now, for this first step here, just reversibly warming up some water, we know that's just Cp times the natural log of T2 over T1, assuming Cp is constant. And remember, in this case, you need to use the heat capacity for liquid water. Then for the actual freezing, we showed before already that delta S for that is equal to the change in enthalpy of freezing, the latent heat of freezing, divided by temperature, obviously. And then, cooling it back down, we already showed before, it's the same formula, basically. Just make sure you put in the correct temperature. This T2 will be 0, this T1 will be negative 10, this T2 will be negative 10, this T1 will be 0. So anyway, and then again, you're going to have to use the heat capacity for solid, H2O, this time. These two CPs not only can be different, they most certainly will be different. So make sure you look up the correct numbers. And again, since it's a state function, the total change in entropy has to be just the change in entropy of all three of those steps. Now, as far as a general change in state, like from pressure 1 to temperature 1 to pressure 2, the volume 2, we did that for an ideal gas already. That's all we can do for now. For general, we're going to have to wait until chapter 4.6 for that. Continuing on physical chemistry, chapter 3, section 4, and continuing with process 10, how we're mixing different inert gases at constant temperature and pressure. So we came up with a formula last time, but we're going to try to simplify it a little bit. So the volume of A, remember, we're assuming ideal gases. So PV plus nRT says that the volume of A is equal to the number of molecules of A times RT divided by pressure. And likewise, for the volume of gas B is going to be NB times RT divided by the pressure. Now the volume then, total, is going to be, of the container, is going to be equal to the total molecules times RT divided by P. And of course, we only have two gases, so the total molecules is just Na plus Nb. And then, so the volume would be Na plus Nb times RT over P. So we're going to simplify that by saying, okay, volume total divided by volume of A, that's going to be the Na plus Nb divided by Na, because all the other RTs, etc., canceled out. And this is going to be equal to 1 over XA, because remember, X of B is going to be NB over Na plus Nb, or XA is going to be Na over Na plus Nb. Remember, X is our mole fraction. So X of A is the mole fraction of A, and X of B is the mole fraction of B. So likewise, the total volume divided by the volume of B is just going to be the number of molecules of A plus the number of molecules of B divided by just the number of molecules of B. So that's going to be equal to 1 over XB. So we know that the natural log of the volume over volume, total volume divided by the volume of A, therefore is going to be equal to the natural log of 1 over XA. So simplifying that, well, distributing it, whatever you want to call it, so we end up with the natural log of 1 minus the natural log of XA. The natural log of 1 is 0, so we can say that's all equal to just minus natural log of XA. And the same process would be true for volume of B. Natural log of volume over volume of B would be equal to minus natural log of the mole fraction of B. So substituting that back into the formula that we had on the previous slide then, our entropy of mixing is going to be just minus Na times R times the natural log of the mole fraction of A minus Nb times R times the natural log of the mole fraction of B. We're going to just pull out the R and combine those, so we get the change in entropy of mixing is equal to minus R times Na natural log XA plus natural log of B times natural log of XB. And that's assuming we have a perfect gas, because we use the ideal gas law, and of course at constant temperature and pressure. What that tells us then, since the natural log of XA has to be less than 1, the natural log of XB has to be less than 1, this double negative is going to make it positive, so the entropy of mixing is going to be greater than 0. Now if you wanted to do something funny and just say, well, what happens if A and B were the same thing? Well, you put that in, and the Na plus ln of XA you're adding it twice, so we pulled that out already. We know that the natural log of XA is going to be equal to 0. So the entropy of mixing is going to, if you mix gas A with itself, of course, would be just 0.